All right, let's take a look at capacitor fundamentals. And so I guess let's start with talking about what is a capacitor. So a capacitor, you can think of it as just two parallel plates. And what we're going to do is that we'd hook it up to a battery, and then we can charge it, and it will accumulate a positive charge on one side and a negative charge on the other. And these are like, just think of them as big plates. Okay, and so let's talk about what a capacitor does. A capacitor stores energy, it stores charge, and then it has the ability then to produce a current if it's hooked into a circuit. And we'll talk about how it's hooked into a circuit maybe in another one, but we're just going to kind of go to the fundamentals of what a capacitor is. And so a capacitor has a capacitance. So eventually we're going to use Q equals CV. We're going to show that a capacitor's capacitance right here is its ability to store charge. So its ability to store charge is its capacitance, and its capacitance is in the units of farad. So farads. And so what is a farad? Well, what would a 1 farad capacitor do? So think of this equation. So this is capacitance times voltage is then coulombs. So then this, a farad, has to be coulombs per volt. Think about that. It's actually kind of cool, right? The bigger the capacitance, the more coulombs it can store per volt. So let's say you had a capacitance of 2 farads and you hooked it up to a battery of 10 voltage, right? Then if it has a capacitance of 2, it means it can store 2 coulombs of charge per volt at 10 volts, then gives you 20 coulombs of charge. Okay, so if we took a battery and we hooked it up to a capacitor, we would charge the capacitor, and we would look at charging that in a much later part of this course. But this would be 10 volts, this would be 2 farads, and a 2 farad capacitor would eventually, over time, accumulate charge, right? The battery would do work to get this charge separation, and it would eventually get the voltage of the battery. And then how much charge would it store? Well, 2 farads at 10 volts would then store 20 coulombs of charge, and then we could use that stored charge to do other things. Okay, so let's talk about how we could figure out the capacitance of something, right? It is some number. How do we get 2 farads for something? So if you want to think about it, it really goes back to Gauss's law in electric fields. What we showed before is that if you look at an infinite sheet of charge, we know that the electric field was sigma over 2 epsilon naught. Okay, and so if we have something like this, well, we know that a capacitor's electric field, the electric field inside this capacitor, well, it's 2 infinite plates, because the positive plate is going to have an electric field that goes this way, but the negative plate is also going to have the same electric field that also goes in the same direction, right? The positives are going to push and the negatives are going to pull, and so the electric field is actually just double an infinite sheet, and so we get sigma over epsilon naught. Sigma, by definition, is the total charge divided by the area, and so we get the electric field inside of a parallel plate capacitor. Again, a parallel plate capacitor is just 2 kind of big plates, which are, we can say, are infinite sheets. Again, we're gonna neglect the edge effects, so we're just looking at kind of inside the capacitor, where we're assuming that it's big enough and it's close enough that we can assume they're infinite sheets. Well, if we know the electric field, we also know that this is a true relationship, that the voltage is equal to ED. Again, this is only true if the electric field is some constant. But we just showed the electric field is constant. It's not a function of the distance here. The electric field is just this. And so then we get that the voltage is Q over A epsilon naught D, and then we want to solve for Q. So Q equals A epsilon naught over D times V. And all of a sudden, we look back here, and that's what we define our capacitance is. That's the capacitance, right? The charge stored on a capacitor is equal to this factor times the voltage, which means this factor is the capacitance. So the capacitance, how you find it, is the area of the plate times epsilon naught over the distance of separation. So how do you make a big capacitor? Well, you want to make a super big plate, and you want the distance between the plates to be really close. Okay, so if you were just constructing a capacitor and you wanted to store a bunch of charge, well, two things. You want to store a bunch of charge, you need a big capacitor, and you also want a big battery. But if you just could focus on the capacitance, then you want a big area and small distance of separation. Okay, so this is how we kind of derived this. There is this thing called a dielectric. Dielectric. And it's some dielectric constant K. And what we do is we would insert some material in here. And what it's going to do is it's going to increase everything. And all it does is increase the capacitance by some factor of K, where K is the dielectric. And you can look on a table and find all these things. But again, inserting this is going to increase the capacitor's ability to store charge by some factor of K, and it's called the dielectric constant. Okay, so this is kind of the fundamentals of capacitors. So this is the main formula right here. What a farad is and how it relates to both the charge stored and then the voltage. This is the derivation of how to find the capacitance of a capacitor. This is how it would look in a very basic circuit with a battery and a capacitor. This is charging. And then that capacitor then has some energy that it stores. So the potential energy, the energy stored, is 1/2 CV squared. You can memorize that. You can take C and put in, remember C is Q over V. So if we put in a Q over V here, that's also equal to 1/2 QV. But if you got rid of the V and you called it Q over C, then it's also then 1/2 Q squared over C. So all three of those versions give you the energy stored, and that kind of just depends on what you're looking at. Okay, so I guess we can look at how they then work in a circuit. So how do they add? So if we had capacitors in parallel, how do they add? And again, I'm going to go through the theory of this, but the total capacitance, if they're in parallel, is the summation of the two capacitance. Okay. If they're in series, okay, this is parallel. That's what we would call things being in parallel. And if things are in series, then they would look something like this. And again, I'm going to go through in a separate video and explain why they add the way they do. But right now, I'm just kind of giving you that idea. In this particular case, the total capacitance, 1 over the total capacitance is 1 over the capacitance of the first guy and 1 over the capacitance of the second guy. Okay, and again, there'll be another video where you can kind of look to see why these two things are true for these scenarios. And again, this is capacitors in series, and that's capacitors in parallel. That's how you find the capacitance of a capacitor. And there are other capacitors. You can have cylindrical capacitors, spherical capacitors. Those are more complicated. Those are things we can deal with later and look up. But 95, 99% of the time, when we're talking about capacitors, we're talking about parallel plate capacitors. Okay. We can do them certainly in different combinations. So we could look at something like this. Something like that. Again, these two are in parallel with each other, and so this capacitance is just C1 plus C2, and that is its own capacitance. Let's call that C4. So this is capacitor 1 and this is capacitor 2, and so what's the total capacitance of this system? Well, these two capacitors are in parallel and they just form some C4, but then the total C, well, this capacitor and that system, well, they're in series, so the total capacitance is 1 over C4 plus 1 over C3. And so you can get some combination. You can get a different combination. If we want to make something like that, so like this is capacitor 1, and this is capacitor 2, and this is, 2, and this is capacitor 3, well then 1 and 2 are in series, so 1 over C4 is 1 over C1 plus 1 over C2, and so C4 is this kind of thing, and then the total capacitance, C, is then these two things are in parallel. Capacitors in parallel just add, so then C4 plus C3 would give you the capacitance. And then again, why do we want the total capacitance? Remember, Q equals CV. Once you can find the total capacitance, and you know the voltage because you know the battery, then you can find the total charge. Once you can find the total charge, then you can start talking about what charge is on each thing. And again, there'll be a separate video where I really go through the examples of making this, 12 volts and 1 farad and 2 farads and 3 farads, and go through numerically how this all works. But this is just kind of the fundamentals. The fundamentals of a capacitor is what makes the capacitor have a certain capacitance, the dielectric constant, the energy stored in capacitors, and then how they add. Again, how they add in parallel, they just add, and how they add in series, they add their inverses. So this will get you started on looking at capacitors.